Hey guys, today I'm going to do a little electrical experiment for you technical folks out there. So what this is basically just a DC supply, but this is 120 volts DC, and what I'm going to demonstrate is how dangerous it is to actually shut off DC voltage. So what you have here is just a regular power cord that feeds a full bridge rectifier. Beautiful thing. That converts DC voltage, 120 volts DC, that's being smoothed out by this capacitor. And what I'm basically doing is I want to touch these two wires. That's supposed to control a 900 watt lamp load, you can say, which I will show right now. So here, as you can see, my array of light bulbs for my electrical experiments and stuff. I'm only gonna turn on 3 light bulbs. These are wired in parallel. You can control each bulb by those switches. So this will give me 900 watts. One of these bulbs is 300 watts rated. So this will give me a nice DC arc. Now what we do is plug it in. Have to always double check, triple check, make sure this capacitor is wired up the correct way, because this is an electrolytic capacitor. And you reverse this. I don't know if you guys ever watch YouTube videos on how capacitors explode, and we're talking about little ones, but this guy's bigger than a pop can, and if this thing blows up, I might as well, better for me if I was underneath the table, because I don't want to get near this thing. So anyway, the capacitor is hooked up correctly. Trust me, I'm an electrician, I know what I'm doing. I have to stand away from this. I plug into my 20 amps receptacle. Yeah, I heard the arc because the capacitor needs a huge inrush current to charge it up. This is live now. So what I'm going to do is watch this. This is going to be interesting. Yeah, you see? See how hard it is to actually disconnect DC? Because when you connect it, it's fine, right? It's normal, but when you disconnect it, that's when it becomes dangerous. Because the voltage in DC never goes to 0. That's why this is arcing like this, because you can't disconnect it, and it's only 900 watts, which is 7.5 amps only. 7.5 amps, not 775 amps or whatever. 7.5. And now what I'm gonna do in my next experiment, I am going to hook up a regular light switch. Such as this. Now first, before I even try to attach the light switch, this is already live with 120 volts DC, or with a peak voltage, which would be 169 volts or something like that around. So what I have to do is I have to unplug it. Unplugging is not enough because that capacitor is live now. It's got the high lethal voltage DC on it. So I have to discharge it simply by just touching it. Stick my voltmeter across it. Set the 300 volts DC. And she's dead. Now I can safely work on it. And always unplug it. Never use a switch because it's just a safer way. But either way, why am I telling you this, people? You should never do this, because this is you have to be an electrical madman like me to actually do experiments like this. So what I'm gonna do is I'm gonna hook up the switch. Now I have my switch hooked up. Turn the lights off for better effect, like the main shop lights. And now we're turning on. See, turning on's not bad. Now watch what happens when you turn it off. Yeah, it's stuck. Oh, that was kind of pathetic. Because the switch is designed so basically there's a little lever that pushes the contacts apart to turn it off, but to turn it on, that just releases those contacts come together with no pressure kind of thing, right? So it's normally closed inside. You need the actual toggle to hold it down to keep the contacts apart. But well, that was a little pathetic. But see if I get another switch. Alright, I replaced the switch. Maybe let's see like if we have like more arcing in this one. I obviously remember to discharge it and everything if I replace it. On. Oh yeah. Not really, yeah. But as you can see, my point is you can't even turn it off. Obviously, I have fire hazard and everything. Let me just shut this thing off because this thing's not designed to run long because that rectifier needs to mount onto a heat. Alright, so I got a duplex receptacle which I'm just replaced the switch with. It's in series with the bulbs. So I'm just gonna get like a power cord like this that has the end shorted out. And just simply plug it in. I'll plug it in the top one because the bottom one's already cooked. Nice. Turn the lights off. And imagine plugging in like a 1200 watt vacuum cleaner into your DC outlet. You can't even unplug it. Look at this. Look at this. What's going on? It's a beauty. The outlet's more promising. Woo! Look at that plug glow. Oh my goodness. Oh my goodness. Turn the fans off. Yeah. See, that's DC, folks. That's DC volts. Very dangerous, very lethal. So basically what this is, like, this is why houses are pumped with AC voltage, not DC, because there'd be a lot of electrical fires. That's why it's a good thing Thomas Edison didn't win the bet between Nikola Tesla. You guys, you technical guys, folks know what I'm talking about. Anyway, so for my next experiment, what I'm gonna do is I'm gonna double up the power. So what I'm gonna do is I'm gonna rig three more light bulbs in series. So I'm gonna have a parallel series connection. And I'm gonna run on double the voltage, which means I'm gonna run off of this 240 volts. I changed the power cord, as you can see. The thing can run on 240 volts AC safely because the rectifier is rated 400 volts DC. And the capacitor is rated 450 volts, which is the peak voltage, which is above the peak voltage of 240, so it's perfectly fine. Now what I'm gonna do is I'm gonna like change the setup with the wiring here that I have going to the light bulbs. Here, as you remember, like there are 3 rows of light bulbs. One row connects the blue wires, all in parallel. Next row connects the black ones. As you can see, the white tape, that's like to indicate which one's a neutral. I don't really care at this point. And the third row is for the brown ones. So now I have the brown ones hooked up. That's the middle row. What I'm gonna do is I'm gonna rig this in series. I'm gonna put, say, black and brown. So I'm gonna put the, like, say, I'm gonna tie the 2 neutrals together, right? And then like at the 2 brown and blacks, I'm gonna put them under the cable now because this cable's not 120 volts DC. It's gonna be 240. So I have brown and black going in, and the 2 neutrals are like, well, not really neutrals, but they're like, you know, if I'm using for 120 volts AC, it's a neutral. I just tie them together. So it's a series parallel series circuit. Also have to make sure with my lamps, so I'm gonna operate these 3 and these 3. So what I gotta do is I gotta turn on my switches. These are on. You can turn that off, off, off. So I have to make sure I have like the same resistance on one leg and on the other one. So it can so it's like a balance, right? So I don't have like a really high voltage across the load that draws less current. Like if I had 4 light bulbs, it would obviously be more current. So the 4 bulbs would glow dim while the 3 would be like really bright and they would burn themselves out. Right, but enough with this theory talk. Let's go fire up this thing. Now, as an electrical madman, I obviously have a lot of stuff on my workbench, as you can see. And I'm also equipped with a European receptacle for my 240 volt applications. Let's plug it in. That's good. It's the 120 volt cord. I can put that aside. Yes. Sure, that's good. That's good. Fire it up. Yeah, I saw the big arc. That's the big arc. Like I saw, like even the power bar flashed inside, because like it needs a lot of current to start that capacitor, because the capacitor it takes a big inrush current to like, you know, get it to fully charge. Once it's charged, it draws nothing. Anyway, now we got this thing in series. We got 240 volts DC, and let's adjust this camera. Now we're gonna stick it in, see what happens. Wish me luck. Oh yeah, the bulbs. And it's stuck. Yeah. Yep. See? That's DC. I took the receptacle off. Obviously, to start this thing up, to plug it in, it's better to like plug into, like, say, my Variac over there. It's an auto transformer. The red cylindrical box, you see. Or I guess I have two of them actually. Now we're gonna do the ultimate DC arc. And see, this is just a relatively high voltage DC. Like, we're not talking about kilovolts, we're talking about, I have to make sure I don't shock myself. This is the load side, so this shouldn't be a big deal. Now we're gonna touch them together. Yeah, see? Yeah. Yeah. The copper's already burnt. Good thing I have a fire extinguisher in my workshop, if anything. Now, while it's unplugged, obviously I gotta discharge it. Because as you can see, the 600 volts. Yeah, this thing's charged, so the way to discharge is touch the wires together. Like that. Check again. Before I put my tongue on it. Dead. I trust my old Simpson meter. Beautiful thing. Yeah, and hopefully you guys like my little electrical experiment. The purpose was because just to show you guys how dangerous the higher voltage DC is. Like, if say you're working on like an electric vehicle or something that has like 60 volts DC or above, like that's what you can, like, you know, that's what you can experience, right? That's why DC contactors have to have special chambers to extinguish the arc. Because turning on is easy, turning off is the hard part. So yeah, hopefully guys like my little video. And yeah, stay tuned for more.